Hello everyone, my name is Nursa Jahan. Today I am going to present the research paper Unraveling Scopes and Challenges in Cardiovascular Risk Prediction using Knowledge Distillation Framework from Clinical to Wearable Sensor Data. We are the authors Nursa Jahan, Nafisa Anjum, Sumit Chakraborty, Evelina Sterling, Najmus Sekib from Kennesaw State University. First, let me give you a little bit brief about this research. Why we need cardiovascular risk prediction. The cardiovascular diseases are the major global concern, causing nearly 380,000 deaths in 2020 alone, and it cost US over 320 billion each year. A key challenge is that traditional risk assessment rely only on occasional clinical visits, giving only brief snapshots of a patient's health. Meanwhile, millions of people use wearables that tracks daily steps, sleep, activity, and offers continuous and real-time data. However, this data isn't yet fully clinically validated, limits the use of risk prediction in the clinical setting. So, our works aim to bridge this gap by using wearable data in a meaningful, clinically aligned way to support early and continuous cardiovascular risk prediction. For fulfilling our aims, we proposed two research questions. So, can a simple wearable-based model learn to detect clinical cardiovascular risk groups identified from lab and EHR data? The second research question is which wearable features like steps, sleep, or heart rate most strongly predict cardiovascular risk. Our proposed solution. Basically, our proposed solution is a teacher-student knowledge distillation-based framework, where our teacher model is an unsupervised clinical phenotyping using EHR-based data. Here we use K-means clustering. And then in the second step, our student model is a wearable-only neural network predicting teachers' phenotypes. And our goal is actually to distill clinical knowledge from teacher model to student model, which is a wearable-based model for continuous monitoring. If we summarize our framework architecture, this architecture basically structured as two steps architecture. First, in the first steps, a teacher model clusters clinical data and it creates some pseudo labels like low, medium, and high risk. And in the second step, student model learns this label from the feed beat based features. And other processing needs for this framework is handling imbalanced data because real life data are too much imbalanced, and for that purpose we use different kinds of imbalance handling techniques like SMOT, ADASIN, or near miss. And then we evaluated the accuracy, precision, recall, and F1 score to understand the performance of this model. So we used the all of us data set, which is which is the data collected from all of us research program. This dataset is consists of diverse population from USA, and the first data we used from the all of us data is lab and measurement data, where we used different categorical data like vital signs, like heart rate, systolic blood pressure, diastolic blood pressure. Then we use metabolic markers like blood glucose, hemoglobin. Then we use other body parameters like BMI, waist circumferences. Then we use lipid profile. Then we use C-reactive protein, renal functions like creatinine, glomerular filtration rate. Then we use hormonal marker like cortisol, electrolytes features, potassium, sodium, and cardiac functions like left ventricular ejection fraction, LVEF, oxygen saturation. And our purpose is to serve a ground truth clinical knowledge for the teacher model from this lab-based data set. And the second data set is Fitbit smartwatch based data set, which are mostly we use the sleep matrices. Then we use activity matrices and heart rate, and we aggregated this data, and then we feature engineered this data. This dataset purpose is to provide continuous real-time physiological data that will be used for student model for knowledge distillation based framework to predict cardiovascular risk. Here we use different kinds of data processing and feature engineering techniques. In this study, we applied outlier removal to capture the data that is continuous data, but that can be noisy, and for such as like sudden spikes in steps count, missing sleep intervals, or sensor dropouts. So we try to remove these outliers to help prevent these errors from biasing the model. And then we use median imputation that allows us to handle missing values in a way that is robust to skewed data and preserves the natural distribution of the signals. Next, we apply standardization because Fitbit derived features come from different scales, like steps may be in thousands, while sleep efficiency is expressed as a percentage. So we need to standardize them to ensure that all variables contribute equally in the learning process. These are important for neural networks, clustering algorithms, or any model that is sensitive to feature magnitude. After cleaning this raw data, we extract Fitbit-derived behavioral and physiological features. These features were selected because they capture patterns that are known to be strongly connected with cardiovascular health, like sleep efficiency and restlessness ratio help quantify sleep quality, which is increasingly linked with long-term cardiovascular risk. Then, deep REM and light sleep percentages provide a more granular understanding of sleep architecture, giving us insight into autonomic nervous system balance and recovery status. Activity to sedentary ratio captures daily movement relative to inactivity, an important predictor of metabolic and cardiovascular health. Finally, we compute aggregated daily averages such as steps, total sleep minutes, and sedentary time, which smooth short-term variation and highlight long-term behavioral patterns. By combining these pre-processing techniques with physiologically meaningful features, we ensure that the student model learns from clean, reliable, and clinically relevant data. So, first step in the teacher model. We used k-means for phenotyping. If you see in the graph, the K means clustering with PCA, that the silhouette score is 0.5653. That means the clusters are very well separated, and we labeled them low, medium, and high CVD risk. These levels are mapped according to their the cluster's physiological parameters like blood pressure, BMI, glucose, or heart rate. These kinds of physiological parameters are analyzed, and they are mapped to low, medium, high. For the student model, we designed a multi-layer perceptron neural network, which is well suited for learning patterns from structured wearable data such as Fitbit features. The inputs to this model are Fitbit derived features we extracted earlier after pre-processing. The architecture includes two hidden layers with 128 units in the first layer and 64 units in the second, both activated using ReLU. This provides enough non-linearity and representational capacity for the model to capture subtle physiological patterns linked to cardiovascular risk. The output layer is designed for three classes corresponding to the clinical cardiovascular risk categories that the student model learns from the teacher model. We use cross entropy loss, which is standard choice for multi-class classification, ensuring the model effectively distinguishes between the different risk groups. For optimization, we chose the Adam optimizer with a learning rate of 0.001, which offers fast convergence and stability, especially when dealing with diverse physiological signals. Overall, this MLP architecture provides a balanced approach, complex enough to capture meaningful pattern in wearable data. But on the other hand, it is also lightweight and efficient enough for potential deployment in the mobile or real-time health application. So finally, after applying our knowledge distillation based student teacher framework, we implemented the baseline framework, and then we handled our imbalanced data with class weights. Then we implemented another version with smooth technique, and then finally we implemented this framework with smooth and did some feature engineering in the feedback data. If we notice in the table on the right side of this slide, we can see the baseline method performed with 73% accuracy, and our final implemented framework with smooth and feature engineering has a accuracy of 66%. So the 73% accuracy is a little bit misleading, because in this implementation, the model actually recognizes the classes from one class mostly, and it ignores the other two minority classes. But after balancing the data set, the final model has an accuracy of 66%, little bit lower, but it can identify the minority classes as well. So here we can see a little bit trade of accuracy and the recognition of the minority classes. Then our second research question was about the feature importance. Our research question was, which wearable features are top predictors for cardiovascular risk? Here we can see the average steps is the highest uh, influencer for this cardiovascular risk prediction, followed by average sedentary minutes, fairly active minutes, and the restlessness ratio and heart rate. These are the top five features that influence the cardiovascular risk classification. Then we try to find out the feature from the clinical data set as well. We implemented a proxy random forest model to understand which features are most important in um, uh, in the EHR data set as well. So here we found out the systolic and diastolic blood pressure, BMI, oxygenation, and heart rate are the dominant features from the lab test data that are mostly important in cardiovascular risk prediction. So finally, the insights from our research work. As we see that this knowledge distillation framework successfully transferred clinical knowledge from teacher model to student model, which is wearable database model, and it can actually recognize the cardiovascular risk classification just like the teacher model. And the performance also improved from the baseline model after we used feature engineering and smart based data balancing techniques. So these models performance can be further improved if we use other techniques as well. But however, there are some limitations too. Pseudo levels are used in this teacher model in this framework, and we need to actually we mapped our labels, but we need to validate these cluster levels too with in the clinical settings. Also, we used smooth based balancing techniques which may introduce synthetic noise. And here actually we used feedback based data's average data, so it may not capture the temporal dynamics completely because we didn't use any time series based model here. Finally, our framework demonstrated the feasibility of predicting clinical CVD risk using wearable data alone. That means wearable based data can also alone predict the cardiovascular risk if we trained and distills the knowledge from the teacher to student model, which is a very simple model but can capture that complex risk as well. We showed that knowledge distillation can enable continuous and non-invasive way of monitoring by using this framework. For the future reference, we could implement time series deep learning like LSTM or transformer based model in feedbit based data student model to understand the temporal dynamics of the data. We could keep clinician in the loop for validation of our framework as well, and then we could use longitudinal risk progression modeling to understand the validation of the long-term and continuous monitoring. And we could use multivariable generalization because we here use only feedback based wearables data. In future we can use another wearables data like Apple Watch or Samsung Galaxy Watch based data. So yeah, so thank you for listening our research paper and our contribution. Thank you all.